All cultures are equal, is the slogan of multiculturalism. But how can this be true? Not even the most avid supporter of multiculturalism can deny that there are large differences between cultures. What they seem to mean, instead, is that all cultures contribute equally to humankind. We don't agree. We think that, during different periods of history, different cultures provided different levels of contributions to humankind's progress. One important element of this progress is the birth of modern science and technology. This happened in the West, in particular in Europe, and nowhere else, mainly during the 16th and 17th centuries. Why did Europe contribute so much to the development of science and technology? Why did the scientific revolution not happen in other parts of the world, for example in China or in the Muslim world? After all, both China and the Muslim world had complex cultures with many important past contributions. The main thesis of this two-part video series is that, by the 17th century, only Europe maintained the intellectual curiosity about the world, which was necessary to trigger the scientific revolution. We'll compare Europe to the Muslim world. To exemplify the differences between these two cultures, we'll show in the first part how differently they reacted to the invention of the telescope beginning of the 17th century. These differences were striking, and in the second part we'll try to identify the reasons for them. There are political implications of these differences between these two cultures, and we'll point them out, too. The main source for the first part is the book Intellectual Curiosity and the Scientific Revolution, A Global Perspective, by Toby Huff. The book title is in the video description below. Towards the end of the 16th century, 4 conceptions of the universe were debated among educated people. The oldest one was the geocentric model conceived by Aristotle in the 4th century BC. It assumed the Earth in the center of the universe. Around the Earth there were a number of rotating spheres. Each of the planets, and also the Moon and the Sun, were attached to one of these spheres and were rotating with it. The outermost sphere contained the fixed stars. The whole universe above the orbit of the Moon is filled with an ethereal, transparent fifth element, quintessence. The heavenly bodies were made of a perfect, unchanging, crystalline substance. The second oldest and most popular one was the geocentric model by Ptolemy, a 2nd century Roman Greek Egyptian astronomer. His model can be seen as an improved mathematical version of Aristotle's model. According to Ptolemy, the Earth was in the center of the universe. The Moon, the planets, the Sun, and the sphere of fixed stars were all revolving around the Earth on circular paths. To account for the occasional backward movement of the planets on the sky, Ptolemy postulated a system of epicycles. This meant that the planets actually followed not one but 2 circular paths. One was the epicycle. It was the center of the epicycle that was revolving around the Earth, following the second circular path, the so-called deferent. Nearest to the Earth was the Moon, followed by the 2 inner planets Mercury and Venus, and then by the Sun. The 3 outer planets Mars, Jupiter and Saturn were outside of the orbit of the Sun. The third model of the universe was the heliocentric model by Copernicus, a Polish scientist, published in his book Revolutions of the Heavenly Spheres in 1543. According to him, all planets, including the Earth, revolve on circular paths around the Sun. The model of Copernicus was able to explain the backward movement of the planets without the assumption of epicycles. To account for discrepancies from real-life observations, both the model of Ptolemy and that of Copernicus have been enhanced by various additional mechanisms. However, as Steven Weinberg writes in his book To Explain the World, both models in their simplest forms give precisely the same predictions regarding the movements of the planets and of the Sun, as they were observable with the naked eye at that time. The fourth model was a hybrid model, proposed by Tycho Brahe, a Danish astronomer, in 1588. According to him, all planets, except the Earth, were revolving around the Sun. The Sun, together with all the planets revolving around it, was revolving around the Earth. Just like the Sun, the sphere of fixed stars was also revolving around the Earth. Tycho Brahe's model was also compatible with all observations made by the naked eye. Aristotle's model was the least supported by evidence and probably was least taken seriously by the late 16th century. But the other three models were more sophisticated. However, based on the data gathered by the instruments available until the end of the 16th century, it was not possible to decide which of these three models was correct. New observations were needed to do that. Enter the telescope. The story of the telescope starts in antiquity, with early attempts to improve human vision. Roman writer Pliny the Elder writes in the 1st century AD that the Emperor Nero used to watch the gladiatorial games in Rome with the help of an emerald. Spectacles were invented in the 13th century, in northern Italy. They were used to correct presbyopia, that is, difficulty in old age of seeing near objects. Spectacle lenses were made out of glass. They were convex lenses, that is, they converged light rays. Mass production of spectacles soon started, and this spread to other European countries too, in particular to the Netherlands. After about 1450, concave lenses became available too. These lenses diverged incoming light rays. They were used in the production of spectacles to correct myopia, that is, the difficulty of seeing far-away objects. However, concave lenses were widely produced only after the end of the 16th century. This might be part of the explanation why it took until the beginning of the 17th century for the telescope to be invented, although both ingredients for building refractive telescopes, that is, concave and convex lenses, had been available for more than 100 years. Given the long history of spectacle making in Europe, it is no wonder that the first usable telescope was built by a spectacle maker called Hans Lippershey, or Lippershey, who lived in Middelburg, in the Netherlands. Lippershey's device magnified faraway objects 3 times. It contained 2 lenses in a tube. The first lens, at the far end of the tube, was used as a magnifier. The second lens, the eyepiece, was used to sharpen the picture produced by the first one. The first lens was convex. Very probably, the second lens was concave, because a convex eyepiece would have resulted in an inverted image. This would have made it not very useful for military and other similar non-scientific applications. When Lippershey demonstrated his device to Count Maurice of Nassau, the commander-in-chief of the Dutch forces, which were at the time in war with the Spanish, the military importance of the device was immediately recognized, both by the Dutch and the Spanish. News about Lippershey's device traveled like wildfire across Europe. A newsletter containing the news was reprinted in Lyon, France, already in 1608. People in different parts of Europe started to copy the idea and make their own telescopes. Some of them, like Thomas Harriot, a graduate of the University of Oxford in England, started using the device in 1609 to observe the sky. Harriot used the telescope to make observations of the moon. He made sketches of the moon's surface but never published his observations. Other people started to watch the moon with their newly built telescopes, too. Alone in Italy there were 5 persons who started doing this already in 1608 and 1609. Galileo Galilei was at that time a professor at the University of Padua, in northern Italy, near Venice. A friend of him read the news reprint and informed Galileo about the new invention, sometime during the first half of 1609. Galileo immediately set to work to produce his own telescope. There was no detailed description of the Dutch design, thus he had to rely on his own reasoning about how it worked. He concluded that it needed to have 2 lenses, a convex lens at the far end of the tube, the objective, and a concave lens as the eyepiece. He produced the lenses himself by grinding glass. His first device magnified faraway objects 3 times. He demonstrated it in Venice in front of officials of the city, to the great amazement of everybody present. Galileo continued making new telescopes, and in the autumn of 1609 he apparently made one with a 20 times magnification. Galileo began to observe the moon using a telescope in the fall of 1609. He made paintings of the moon's surface. This showed an important thing: it looked as if it had mountains, valleys, and other features familiar from landscapes on Earth. Why was this observation important? Because it contradicted the idea, shared by most educated people in Europe since Aristotle, that the moon is a perfect crystalline sphere. Galileo's observations showed that the moon might be much more similar to the Earth than anybody expected. Maybe the heavenly bodies, then, are made of the same material as the Earth, obeying the same laws instead of being fundamentally different. Next year, in January 1609, Galileo turned his telescope towards Jupiter and made another discovery. Through the telescope, Jupiter appeared not just as a point of light but as a round planet. Even more startling, it seemed that around Jupiter there were 4 other small, previously unseen, planets. Galileo observed that these little planets were revolving around Jupiter. In other words, Galileo discovered the moons of Jupiter. Soon thereafter, Galileo made a further revolutionary observation. He discovered that the Milky Way was not just some kind of white vapor in the sky, but that it consisted of many stars, previously unseen. He published his observations in March 1609 in a little book, titled Sidereus Nuncius, or Starry Messenger. The book caused great excitement and lots of debate all over Europe. In the hands of Galileo and of other scientists in Europe, the telescope started to break down age-old ideas about the universe and provide evidence for a fundamentally new worldview. There were more startling discoveries to come. In the summer of 1610, Galileo turned his telescope towards the Saturn. Around that planet he saw something that looked like some kind of handles on both sides. He thought that it looked as if the Saturn is not a single planet but a composite of 3 planets. Of course, what he discovered were the rings of the Saturn. However, what exactly these handles were would remain a mystery for half a century, until more powerful telescopes were available. But the discovery with the farthest-reaching consequences was still ahead. Sometime in the autumn of 1610, Galileo started observing the planet Venus. He observed that Venus had phases, similarly to the moon. In other words, depending on its location in the sky, part of the disk appeared in a shade, sometimes giving it a horn-like appearance, sometimes a fuller appearance. One of the phases was a full Venus, shown as a full circle in Galileo's drawing. The models of Ptolemy, Copernicus, and of Tycho Brahe were all compatible with phases of the Venus. However, the Ptolemaic system predicted a different pattern than the Copernican system or the system of Tycho Brahe. The left-hand part of the image shows the predictions of Ptolemy's model. The right-hand part shows predictions of the model of Copernicus. The actual predictions about the phases of Venus are shown in the top area of both parts. One clear difference between the two models is that Ptolemy's model doesn't predict a full Venus, shown as a full circle, while the model of Copernicus does. As Galileo observed a full Venus, his observations supported the predictions made by Copernicus. Galileo's observations were also compatible with Tycho Brahe's hybrid system, in which all the planets, except the Earth, revolved around the Sun, and the Sun, plus the sphere containing the fixed stars, were revolving around the Earth. Thus, Galileo's observations did not provide evidence to decide between the Copernican system and Tycho Brahe's system. Such evidence will come forward only much later. Using the telescope for scientific inquiry almost as soon as it was invented, Galileo provided decisive evidence in favor of the heliocentric Copernican worldview and against earlier views, in particular against the geocentric Ptolemaic worldview. But he was not alone in using the telescope as a scientific instrument. Already in 1610, other astronomers started to try to replicate his findings. Because of the low quality and low magnification of these first telescopes, Not everybody succeeded to confirm Galileo's observations. However, others did succeed to confirm them. This caused a debate about these phenomena among scientists. The mathematician and astronomer Johannes Kepler suggested a design to improve on Galileo's telescope in 1611 by using two convex lenses instead of one convex and one concave lens. This design resulted in a much wider field of view and in higher magnifications. It was quite useless for terrestrial, for example military or naval use, because the magnified image was upside down. However, this didn't matter when the device was used for astronomical purposes. Kepler didn't actually produce a telescope like that, but Francesco Fontana, an Italian astronomer, did so during the late 1620s. He used it to investigate the surface of the moon. But Kepler's telescope had problems, too. In particular, the image delivered by the device showed interfering rainbow halos, chromatic aberrations. It was found that this could be corrected by making very long focal length objective lenses. This resulted in very long telescope tubes. Increasing the diameter of the objective also required longer tubes. One such telescope was built by Johannes Hevelius in Poland in 1673. Other people found that they did not need a tube at all to build such long telescopes, and created so-called aerial telescopes. Astronomer Giovanni Domenico Cassini used such an aerial telescope at the Observatory of Paris in 1684 to discover two moons of the planet Saturn. Cassini also described markings on the surface of the planet Mars and determined the rotational periods of Mars and Venus. All these telescopes were of the refracting type, using lenses for magnification. However, Galileo and others soon started thinking about designs using curved mirrors instead of lenses for magnification. English scientist Sir Isaac Newton built the first such reflecting telescope in 1668. Reflecting telescopes eventually became the standard for astronomical research. While all this research using the telescope was going on in Europe, making momentous discoveries about the universe, what was happening in the Muslim world in the area of optics and its applications? There had been a venerable tradition of such research in the Muslim world. Ibn al-Haytham, or al-Hazm with his Latin name, made important contributions to optics in the 11th century. Among other things, he described the visual pathways in the brain, came up with an influential theory of vision, and experimented with lenses and mirrors. His book of optics has been translated into Latin in the 12th or 13th century. However, this scientific tradition was not continued. Also, it was not translated into practical usage. When spectacles appeared in the Muslim world, they were imports from Europe. Thousands of pairs of spectacles were shipped from northern Italy into the Ottoman Empire from the 15th century onward. For example, in 1540 24,000 pairs of spectacles were sent from Florence, in northern Italy, to Istanbul. In the 16th century, the Portuguese started exporting spectacles to Muslim-ruled northern India. This was followed in the 17th century by the British East India Company, which gave spectacles as presents to high-ranking members of the Mughal court and was also selling spectacles in India. Thus, spectacles, and with them the basic ingredients of telescopes, were available in Muslim lands for hundreds of years. But there is no record about Muslim craftsmen or scientists attempting to create telescopes, just as in the case of spectacles. When telescopes appeared in Muslim countries, they were imports from Europe. Just like optics, astronomy had an illustrious tradition in the Muslim Middle East. Muslim astronomers like al-Barani, al-Tusi, and Ibn al-Shatir, all of whom lived between the 10th and 14th centuries, were creating astronomical tables and cataloguing stars. Many of them were gifted mathematicians and came up with new models to try to improve on Ptolemy's system. They all worked within Ptolemy's geocentric paradigm. Though they did improve Ptolemy's model, they never moved towards heliocentrism, as Copernicus did later. Astronomical observatories were built, as in Baghdad, under the Abbasid Caliph al-Ma'mun in the 9th century and in Cairo in the 12th century. During the 13th century, the Mongol warlord Hulagu Khan, the destroyer of Baghdad, established an observatory in Marika, in current-day northwest Iran. In the 15th century, Ulugh Beg, a descendant of another Mongol ruler, Tamerlane, built an observatory in Samarkand, Uzbekistan, in Central Asia. The Ottoman Sultan Murad III also built an observatory in Istanbul in the 16th century. In the Muslim Mughal Empire in India, the Hindu ruler Jai Singh built an observatory in Jaipur in the first half of the 18th century. Some of these observatories, like the Marigu Observatory under the direction of Al-Tusi and the Samarkand Observatory of Ulugh Beg, became famous for the research that was undertaken. At all of these observatories, astronomical observations were done by the naked eye. Sophisticated instruments were also used, like the huge sextant, part of which was cut into a rock, at Ulugh Beg's observatory. The Jaipur Observatory also contained a large sextant, modelled after the one at Ulugh Beg's observatory. What happened to these observatories? With the exception of the Jaipur Observatory, which was built later, none of them were functional by the 17th century. Some of them were abandoned after the ruler who founded them died and when later rulers lost interest in supporting them. Other observatories were destroyed. Murky political conflicts, enhanced by Islamic religious resistance to the work done at the observatories, were the causes for the destruction of the observatories. One source of the religious resistance was the fear that the observatories were used for astrological purposes. The Baghdad Observatory was abandoned in the 9th century, after about 30 years of existence. The Cairo Observatory of Al-Ma'mun was destroyed in 1125, after only 5 years. Work ceased at the Marigu Observatory after about 50 years for lack of funding during the 14th century, although maybe frequent earthquakes also played a role. The Samarkand Observatory of Ulugh Beg was destroyed in 1449, 21 years after it was built, when Ulugh Beg was assassinated. The Istanbul Observatory was destroyed in 1580 after only 3 years of existence. After this, no significant observatories were built in the Ottoman Empire until the 19th century. The Jaipur Observatory was abandoned after 9 years of existence, when Jai Singh died in 1743. Paralleling the fate of the observatories, not much has remained of the once proud astronomical tradition of the Muslim world by the 16th and 17th centuries. During the 17th and 18th centuries there were 3 large empires in the Muslim world: the Mughal Empire in India, the Safavid Empire in Iran, and the Ottoman Empire in the Middle East, with territories also in North Africa and Southeast Europe. In this video we'll look at the story of the telescope in the Mughal and Ottoman empires. In the Mughal Empire in India, the first telescope was apparently introduced by the British in 1615, 7 years after the telescope was invented in the Netherlands. After that, telescopes were owned by a number of Europeans living in India at the time. Some of them used it to make astronomical discoveries. Telescopes were also known to some high-profile Indian officials. Despite this availability of telescopes in India, no Mughal scholars undertook to use the telescope for astronomical purposes in the 17th century. The Mughals did have an interest in astronomy, but apparently not in new methods or tools which might challenge age-old astronomical models. Or maybe they were not interested in detailed scientific models of the universe at all. Thus, the Jaipur Observatory, mentioned before, didn't employ telescopes, despite the fact that at the time this observatory was built at the beginning of the 18th century, telescopes had been around for more than 100 years. Instead, the Jaipur Observatory emulated Ulugh Beg's Samarkand Observatory built 300 years before. Eventually, it was the British who built the first modern observatory in India. Built by the British East India Company in Madras in 1792, the observatory employed impressive telescopes. In the Ottoman Empire, the other great Muslim empire, the first mention of a telescope is from 1630, when a Venetian merchant was hanged by Sultan Murad IV because he used a telescope to spy at the harem of the Sultan. 20 years later, in the middle of the 17th century, telescopes were quite well known in the Ottoman Empire. They were used in the Ottoman Navy. Turkish and European travelers used telescopes, and they could be bought in Cairo, Egypt, too. However, similarly as in India, there is no record of telescopes used for astronomical observations until much later. The story of the telescope in the Muslim world in the 17th and 18th centuries is in sharp contrast to what was happening in Europe during the same time. Immediately after the invention of the telescope, Europe was experiencing an outburst of scientific curiosity. European scientists started using the telescope to learn more about the universe. Momentous discoveries were made almost at once. Research findings were published in books which were read all over Europe. Problems with the telescope were identified and improvements in design were made. The impression is an almost feverish activity to increase knowledge about the universe and to create and improve on tools which help in that activity. In contrast, the Muslim world gives the impression of being stuck in the Middle Ages, not open to new ideas. After impressive astronomical achievements during the Middle Ages, this part of the world seems to have lost its spirit of scientific curiosity by the 17th century. Astronomical observatories disappeared, either because founding ceased for them or because they were intentionally destroyed. In those observatories which did remain, research methods were oriented towards the legendary past. This was the case at the Jaipur Observatory in Mughal India, which tried to emulate Ulugh Beg's observatory instead of using telescopes. This lack of scientific curiosity resulted in a swiftly widening gap between Europe and the Muslim world regarding scientific knowledge and achievements. Toby Huff writes in his book Intellectual Curiosity and the Scientific Revolution. When the telescope arrived in the early 17th century, Muslim astronomers paid no attention to it. There is no indication that Middle Eastern scholars used the telescope for astronomical exploration, or that Muslim scholars were in search of or open to new theoretical ideas in astronomy. Indeed, the shift to a Copernican or Newtonian worldview was greatly delayed in the Middle East. Why did this happen like this in the Muslim world? And why was the development in Europe so different? This is the topic of the second part of this video series.